So that's the motoring cycle. So the coil turns on here, it sucks it up, turns off here, and it lets it drop out. Electrically, when the coil turns on, it draws power from the power supply, and when it turns off, the circuit allows the discharge of the magnetic field to create an inductive collapse, and that energy is siphoned back through a secondary circuit to charge this battery in the back. So we can not only we can take electricity from here, create mechanical energy here, and get electricity back over here. And that all we have to do is stagger these events in time so that they don't oppose each other at any given time. So let's see how it works. So I've got the power supply dialed up to about 12 volts, and you can see that the current is jumping around because this samples faster than this is turning on and off. Well, you can see that we've already pushed our battery up from where it was before, and it continues to climb. Now, the amount of energy that this draws is specifically related just to the resistance of the wire in the coil and the duty cycle of the commutator. So no matter how fast or slow this turns, it's going to draw exactly the same amount of energy. Now, there's a number of things that determine how much mechanical force is produced, and primarily it has to do with the efficiency of the magnetic circuit. Right now, this is in its absolutely worst condition because the magnetic field is wide open to the environment. But it still is enough to draw the piece of iron in. Now what we've done is we've built this little iron keeper here. This is just to get it, we can put this directly around the coil. And this is just some plastic pieces that we filled up with iron filings and glued together so that we can stick this down here and start folding this magnetic field down around itself so we can get a better magnetic circuit going. This is just a piece of junk that we pulled off the shelf, but it has an iron here, and as soon as I put this on the top and really start folding this magnetic field down, you can see that it speeds way up. Now, what this means is that the coil is turning off more often, many more times per second. The faster this goes, the more times the coil turns off per second, and so it charges the battery faster, even though we're still not drawing any more from over here. And now you can see that at this speed, we can see that the current has really settled down to about 2.3, 2.4 amperes, and that's what the system draws to run the motor. Now, what I'd like to do is, and we're pushing the battery up to 13 volts. Now this battery is fairly well charged, so it's not too difficult to push it up here because this battery is almost fully charged as it is, but this illustrates the point. Now the other thing I want to show you is you can see that the current basically is centering right around 2.3. And if I raise the voltage just a little bit and make it go a little bit faster, then we can get it to stabilize at, say, about 2.3, 2.4, and so that's where the current is. Now, we saw with the other motors, the minute that I would try and slow this down at all, then the current that it was drawing would jump up completely. But now on this motor, if I slow it down, you see that the number doesn't just go up, it also goes down, so it's still jumping in the same range. And again, we're into that sampling problem again. But basically what happens is that the duty cycle of the resistance of the resistance of the coil stays the same, and the duty cycle of the commutator stays the same because it's on the same amount of time, same percentage of time, whether it's going fast or slow. So the total amount of current is determined by those two factors and those two factors alone, and not in relationship to what the mechanical load is. So here we have a much more interesting motor that shows the principles that I was talking about when we were looking at the standard motors. Here we have a way of taking electricity, creating a motor torque, and getting some of the electricity back in a way that doesn't generate electricity against itself and cause a reverse motoring effect that slows the motor down or makes the motor draw more current when we mechanically load it. Now what I'm going to do next is I've got this little belt, and I'm going to attach this belt to our flywheel over here and attach it to this little permanent magnet DC generator over here. So I'm going to start driving this as a generator from our motor. Okay, and okay, so I'm going to do that. Okay, and so I've got this at about 16, maybe I'll crank it up a little bit more. And what I want to show you, so I've got this running at about 17 volts, and as you can see, the current it's drawing is right around 3.3. But now what I can do is, and now see we're turning it off and on so often, but it's really starting to push this battery. But now what I can do is, I can ask this generator to run a load. And as you can see, it slows it down, actually asks it to do work, but the total amount of current that is drawn from the power supply stays basically in the same range. It stays centered in the same range. So again, it doesn't immediately jump to twice or anything else. And so this is a perfectly good demonstration that shows that it is possible to build an electric motor that creates mechanical energy, gives you some of the electricity back, and operates with no back EMF in the sense that as a motor, it's only a motor. Now the reason this doesn't draw more energy when it's drawing a load is that, one, it doesn't act as a generator. I can twist this all day and all night, and it doesn't generate anything. Okay, it generates over here, but this process of moving an iron shaft in and out of a coil will never generate any electricity. So this is only an electric motor, and it is not a generator in reverse. So the fact is that the only thing determining how much energy this device will draw is the resistance of the coil and the duty cycle of the commutator. It has nothing whatever to do with how much mechanical energy I can harvest from here. It's completely out of the equation, okay? Now this motor is not particularly efficient, and one of the main reasons, you could see that when I put the topper on here, it started going a lot faster without drawing any more electricity, and shows you that the amount of mechanical energy I can get out of this is really somewhat independent of the amount of electricity that it draws. Now, we're probably missing out on about 50% of the mechanical energy that this thing could produce, because when we built this originally, you can see that we glued the coil directly down to this piece of plastic. So there's no way to finish folding the magnetic field down around the bottom of the coil so that we can really tightly wrap this magnetic field all the way around so that it's very, very efficient. We could probably get 50 to 60% more mechanical energy out of this for the exact same amount of electricity burned if we were able to do that with this model. So again, this shows a number of very important aspects to this, but again, this particular model has problems which can be corrected by an adjustment in the design. So here we have excellent evidence that the motors that we were looking at originally, the kind you can buy off the shelf, and that they are behaving the way they're behaving because of the geometry of the parts. And this one clearly shows that. And in fact, all motors and generators behave the way they behave because of the geometry of their component parts, and not because they're limited by some, definite need to follow the laws of thermodynamics or anything else. Each one of these devices is specifically designed to behave in a particular window, and that's what they do. And they do that because of the geometry of the materials as they were designed into the motor design itself.